This week is the 237th meeting of the American Astronomical Society, one of the biggest astronomy events of the year. I went to my first AAS meeting in 2019 as a PhD student, which is pretty much where I got my current job. This event blew me away. There were literally thousands of astronomers swarming around the Seattle Convention Center, something that I'd just never seen before. Back then, I presented my work on finding explosions in the Kepler Space Telescope data. This year I'll be talking about something kind of similar, a project I've been working on to let anyone analyze cosmic explosions that were observed by the Transiting Exoplanet Survey Satellite, or TESS. So TESS spends its days in an extremely precise orbit between the Earth and Moon, going around once about every 14 days. It doesn't take any stunning pictures like, say, Hubble, but it does watch an enormous 2,300 square degree slice of the sky. To get a better understanding of just how big this is, let's ask Vegeta how many full moons would be able to fit inside of that slice of sky.
It's over 9,000! What, 9,000? There's no way that can be right!
No, Nappa, Vegeta is right. TESS watches a slice of the sky around 9,200 times the size of the full moon. For the first few years, it imaged these strips of sky every 30 minutes, so if something changed while TESS was watching it, then we could get a really good idea of how that object changed over time. Although TESS was designed to detect exoplanets, it's fantastic at watching stars change as well, and especially stars that are exploding at the end of their lives. And this is where I come in as the ever-morbid astronomer hunting for the final moments of a star's life. TESS has observed hundreds of supernovae by now, which is fantastic for me, but since nothing is ever easy in science, actually finding the supernova signal in TESS data is a massive challenge. What we're looking at now is something called a light curve. It's a graph of how the brightness of an object changes with time. The brightness is on the vertical axis and time is on the horizontal axis. So with this TESS light curve, we can indeed see that the brightness changes over time, but pretty much all of this signal belongs to something much more familiar. These big spikes are not from some far-off exploding star, but light being reflected off the Earth into the TESS cameras. In fact, a few years ago, Rodrigo Lugo had an April Fool's paper that told us you could actually work out some surface details of the Earth based off the light that was scattered into TESS. But anyway, I don't want this light from the Earth, so we need to get rid of it. But it turns out getting rid of this light is kinda tricky. To TESS, stars and galaxies are all kind of blended together in this low-resolution image. So finding patches of mostly empty sky to determine the background scattered Earth light from, say, the supernova light is actually pretty tricky. There are also lots of other fun complications that make this even harder, like the background varying with time and varying across the detectors. But after a while I wrote some code that mostly works and removes pretty much all of the background light, which enables me to see the supernova, which oftentimes is hundreds or thousands of times fainter than the scattered light that TESS detects coming from Earth. In this example, the blue line is the original TESS light curve, and the orange is the light curve with the background subtracted. You can see just how big the difference is. If we just focus on the orange line, what looked like a flat, featureless line is actually something a bit more complicated. It starts out low and it gets brighter as time goes on. It changes. What we have here is the light curve of a Type 1a supernova called 2018 FUB. At the start of the light curve, it is flat because the supernova just hasn't exploded yet. Then all of a sudden, it starts increasing in brightness, which of course tells us that the star blew up. Since the background is so much brighter than the supernova, removing it accurately and reliably is really important for anyone who wants to study these kinds of things. Alongside the challenges of subtracting out the background Earth light, in a lot of these cases we actually need to shift the images around a little so that they actually match up. This part just involves identifying a bunch of stars in the TESS images and watching how they move image to image, and then just reversing how they move image to image. All of these analysis steps can be pretty tricky and prevent people from doing science with TESS data, so I've been writing Python code to allow anyone to quickly correct TESS light curves. All you need to do is put in the coordinates and then set it loose. Once you have the light curves, you can analyze them to your heart's content. So with my tool, hopefully more people can do science with TESS data. At the AAS meeting this week, I'll be giving a talk about how this all works, and maybe someone will find it useful and it will let them do science that they weren't able to do before. But as well as talks at conferences, there are also lots of scientific posters. Posters are actually a pretty big thing in science. In general, they try to present the science in a pretty compact way that anyone could make sense of. It's definitely an art form in and of itself, so it's always interesting to see what people have discovered, and as well how they present what they discovered. During this week's AAS meeting, there will be hundreds of posters, so I thought it could be fun to explore them together on a live stream. The Science Poster stream will be happening Thursday the 14th at 4 PM Eastern Standard Time. A link to the stream will be down below, so come along and join me if you're interested in learning about some of the newest discoveries in astronomy. I really hope to see you there, and I am really looking forward to seeing what posters we'll come across. But for now, thanks for watching.